So question 3 was mostly a circular motion question. It's about this amusement ride, specifically a chain swing ride. And it's basically, this disc is moving in a horizontal plane, so this is horizontal circular motion. And people sit in seats which are attached freely by inextensible chains of length 4.3 meters to a fixed points on the disc. So you can see it in the diagram. We'll read through the rest first. So it hangs from point X on the ride and makes an angle alpha with the vertical. X is 3.5 meters from the axis of rotation, which is the vertical line PQ, and the chain is free to swing in or out relative to PQ. The ride rotates about PQ with a constant angular velocity omega. Seat A moves in horizontal circular motion, a horizontal circular path which is 6 meters above the ground. So, as you can see, we have the 3.5 meters as a little, I suppose, the radius between the center of rotation and the point X, but then seat A is a little bit further out, as you can see by this triangle here, and seat A is also 6 meters above the ground, but that's not relevant quite yet. So draw a diagram to show the external forces acting on seat A. Well, okay, so there's really only two. Of course, everything that has mass will have its weight pulling it down. Its weight, and weight is mg, as you know. You wouldn't really have to write this in, but just be specific. And then we'd also have the tension force from the chain. So why isn't the chair falling down? Well, it's because the tension force is keeping it up in the air. It's counteracting the weight force. Now we can resolve that tension force by drawing dotted lines. And remember, this angle here is alpha. So this is going to be t cos alpha, because this is the one beside the alpha. And this one down here is going to be t sine alpha. I don't think you'd have to resolve it, but just in case, there it is. And there are all of the forces. Now, part 2 is a bit of a mouthful, but it says to show that omega is the square root of g tan alpha over 3.5 plus 4.3 sine alpha. Now, I'd say this probably scared a lot of people off, but it's actually not that bad. So in order to utilize this, first of all, we're going to need to know the equations for circular motion, the formulae. And they're all on page 51 of the Formulae and Tables book, but I'm going to just be referring to them. So the first thing we need to do is we need to find, well, seat A, what's the radius? What's the distance from seat A to the middle? Because if something's moving in horizontal circular motion, we need to know how far away from the middle it is. How can we figure this out? Well, we have a right angle triangle here in the diagram. If I just extend this down, we know the hypotenuse is 4.3, and we know that we have that angle alpha there. So let's just redraw that. So we have, this is 4.3, and we have alpha here. So what's this distance here going to be, the horizontal distance? It's going to be 4.3 sine alpha, because it's the opposite of the alpha. Therefore, the radius is going to be this 3.5 plus the 4.3 sine alpha here, because that's the distance from the center all the way over to A. So we can write that down. And now you can see it's starting to match up with the thing we have in the question, the 3.5 plus 4.3 sine alpha. But we'll continue anyway. So now let's just have a look at the forces again. So in horizontal circular motion, we have two main things we need to do. First one is forces up will be equal to forces down. So that means the t cos alpha in our diagram has to be equal to the weight mg. And that's our first thing we do. And then the second equation you'll do is about the centripetal force. So since we're looking for omega, we're going to use the definition that has omega in it. So it's m or omega squared. That's going to be equal to the centripetal force. What's the centripetal force? Well, it's going to be all the force that's keeping it in the circle, the force that's dragging it towards the center of the circle. And in our diagram, that's just t sine alpha. The rest of them, t cos alpha is going up and the weight's going down. So the centripetal force, m or omega squared, that's going to be equal to t sine alpha. So now, if we have a look at what we need, we don't have a t in that answer that they want. So we can get rid of the t by using our equation 1. We can say that t equals mg divided by cos alpha. And now we can put that into here, into our second equation. So we're going to have m or omega squared equals mg over cos alpha times sine alpha. So those m's are going to cancel. We can divide by m on both sides, and m won't be 0. Or, we know or, well, we'll just leave it as or for now. But now we have or omega squared equals sine over cos is just tan. And we have the g, so we're going to have g tan alpha. Now we can divide by or and take the square root on both sides, giving that omega equals the square root of g tan alpha over or, and we know what or is. So we have the square root of g tan alpha. And what's or? Well, let's have a look at the start. We said it was 3.5 plus 4.3 sine alpha. So over 3.5 plus 4.3 sine alpha. And that is it. That's what they wanted us to get, as you can see. So even though this part seems simple, it actually tripped me up a bit. So it says use dimensional analysis to show that this thing is equivalent to the units for omega. So I thought the unit for omega was radians per second, but in reality, if we have a look at the formulae, omega is theta divided by t, where theta is the angle and t is the time, and theta is just the arc length divided by the radius. Arc length is meters, radius is meters. Theta is actually dimensionless. It doesn't have a unit. So this is actually no unit over seconds. So the unit for omega is just inverse seconds. It's just per second. So omega will be in inverse seconds, or you could write that as 1 over s if you want. But s to the minus 1 just is easier. So inverse seconds will be equal to the square root of g is acceleration, so that's meters per second squared. Tan alpha is just a number. Now this 3.5 plus 4.3 sine alpha, well, remember, that's what we said our radius was here. So that whole thing has a unit of meters. Because remember, that 3.5 is from the center to x, and then the 4.3 sine alpha is from x to seat A. So that's all a distance, that's meters. So now this is going to be meters divided by meters. They're going to cancel, giving us inverse seconds equals the square root of s to the power minus 2. And the square root of that will give s to the power minus 1. So that's tick, they're the same. So now we're told that alpha equals 25 degrees, and we're asked to calculate how many complete revolutions the ride makes in 1 minute. So we know our angular velocity is the square root of g tan alpha over 3.5 plus 4.3 sine alpha. So we can now get a number on that. So omega will be the square root of g tan alpha all over 3.5 plus 4.3 sine alpha. And I guess instead of writing alpha, I'll just write it in 25 now. And remember that it is 25 degrees, as it says up there. So it gives an angular velocity of 0.927 per second. I guess the unit doesn't really matter, but whatever. So what does this mean? This means it's doing 0.927 radians every second. Now, how many radians are in a full circle? Well, there's 2 pi radians. And if we divide that by 0.9727, it's 2 pi radians divided by how many radians it can do per second. So that gives us 6.778. So what does this mean? Well, it takes 6.778 seconds to do 1 revolution. Because, again, we're doing a full circle of 2 pi radians. Divide that by 0.927 radians. We're seeing how many times does that 0.92... How many of those 0.927s do we need to get up to the 2 pi, to get to the full revolution? So that means it'll take 6.778 seconds for a revolution. Now it says, how many complete revolutions does it make in 1 minute? Well, 1 minute is 60 seconds, divided by 6.778 seconds, giving us 8.852. Now it says, how many complete revolutions does it make in 1 minute? Well, it makes 8 complete revolutions and then 0.852, so that means 8 complete revolutions. So the last question is actually just a uniform motion question. So basically, a person in seat A throws a small orange up, and they give 4 meters per second to the orange going upwards. How long does it take until it hits the ground? Well, let's have a look at our diagram. A is 6 meters above the ground. So in total, starting from the starting point, it needs to go down 6 meters. So since it needs to go down 6 meters, the displacement will be minus 6. The initial velocity is 4 upwards. The acceleration is minus g. And the time taken is what we're looking for. So SUAT, that's S equals UT plus a half AT squared. So minus 6 equals 4T minus GT squared over 2. Now we can rearrange this to get a quadratic in T. So we can say that 4.9 T squared minus 4T minus 6 will be equal to 0. We could try to factor this, but we won't. We'll just use the formula. T equals the quadratic formula, so it's negative b, which will be 4, positive 4, plus or minus the square root of 4 squared minus 4 times 4.9 times minus 6, all over 2 times 4.9. So if we do the plus, we'll get 4 plus the square root of 133.6, all over 9.8, and that's equal to 1.588 seconds. And if we use the minus, we'll get 4 minus the square root of 133.6 all over 9.8, and that'll give us minus 0.771. So of course the second scenario isn't possible, therefore it has to be 1.588 seconds.